Let's see, are we live now? Ooh, what the fuck? What the fuck? Okay. So apparently FFmpeg cannot really stream from a configuration where I have the screen. I actually have one of the screens slightly offset because it is offset in reality. So I find it very nice to have it offset in software as well. Let's see if I can fix this. This is actually something that I think I can fix using the by adjusting the settings that I use for FFmpeg. So let's see here. I could I'm just going to edit this script that I use. Let's see, stream. Unfortunately, you cannot see what I'm doing because my screen is totally messed up. Maybe I can do it here. Let's see. I can probably move this external a little bit. Let's see. Stream. Oh, yeah, we could do that. Let's see. So, here I have position. So I'm grabbing the X11 and I'm using position. I think this is like the display and the position. So probably what I need to do is adjust this position. I'm going to try that. Let's see. The trick here is to find the actual position that it's offset by, which I don't really know, and I don't really know how to find it either, because this is all done like visually. So this is how I have my screens. So I need to like figure out what position it's on. I guess I could make a guess. So I could say maybe it's roughly one. Maybe it's not 2/3, it's slightly less than 2/3. So maybe if I divide it by, let's see, divide it by 4 and multiply it by like 2.5. So let's see here. So I got 1920 divided by 4 times 2.5. 1/200. Maybe that works better. So we'll move this to 1/200. Let's see if this works better. I wonder if I can stop the stream and then restart it without losing the connection. Okay, let's see if this works better. Yay! My screen is streamed properly. Okay, so the way I found the value to put there is by looking at the error messages I got from FFmpeg. Because when I put 1/200 there, it actually complained that the position was not within the screen, and then it like told me the actual size of the screen. So I just subtracted 1920 from the value I got, and I got 1152. And now it seems that my screen is streamed in the full size. So great. Now I can work with the offset screens, which makes things very practical for me. Right, so today I'm going to start with coding the clock code. I'm going to be improving the RCC initialization because I think it's a total mess. In the STM32, the parts of the CMSIS that are responsible for setting up the clocks, they are very. It becomes hard to kind of run the same code on multiple targets with different clock settings, with different crystals, and with different maximum frequencies. So what I want to do is I want to make sure that the clocks are configurable from the device tree. It gets a little bit tricky because let's just open the code and see. So I can close this, and I'm just gonna close my other terminal so I can reopen the code in here. Let's see. I started using NVim as well. I think NVim is a really good improvement on Vim. Many nice features, like the UI is slightly improved. I haven't really discovered all the features yet, but I can definitely see little differences, little details that are different from the standard Vim. Like installing plugins is really simple, yeah, it seems plausible. It's going to be very good improvement. Let's see. So let's have a look at the system file. So this comes from the STM32 libraries, and this is the system. This gets called from the system init, and I have commented this out because I wanted to see what happens if this is not actually running. And what happens is that STM32 will run from the internal oscillator, which is 16 megahertz, and that works fine. So we can actually use that oscillator until we initialize the external oscillator and switch to the PLL. And this fact is important because I'm running on top of free RTOS, and it's important for me that all the drivers are started from the init thread. So I can't initialize the drivers before that, because some of the drivers, they actually start services, and I want those services to start running before the call to the before the call to the start scheduler, which actually starts all the threads. So if I don't run the drivers from a thread, then the free RTOS is not actually running. So the threads won't start in time, and that's a problem. So the way I've done this is that in my very simple, like basically everything ends up being a driver. So this is a very simple main that just calls. It starts one thread, then starts a scheduler, and then it probes the device drivers. And the majority of the code, and even the application code, goes into device drivers. And this actually loads the device drivers through the device tree, which means that everything is configurable through the device tree. For this board, I can open the device tree that I started writing here. I've got some basic stuff running on this board. This is a small board, which you've seen in one of my previous videos. It's one of these. Let's see. It looks like this. So this is a small optical flow board, and it's blinking a LED. So it means that the free RTOS is running fine. And I'm going to be extending this board with other device drivers that are going to take care of all the devices on this board. But I want to fix this clock functionality first, because I want to be able to write in my device tree like this. I would define my CPU, and then I want to specify the HSC value, which would be, in this case, 8 megahertz. And then I want to specify the H clock div, which is the divider for the main system clock. So we would have, or actually no, H clock div is for the AHB bus, to which many of the like pretty much all the peripherals are connected. I think I have to actually check the clock tree to be able to tell you for sure. But there's a number of settings that need to be configured for each particular chip, and it's very impractical to do this from the code. I have to write generic code and make sure that all of this is configurable from the device tree, and that will make sure that I don't have to make any changes to the code to run it on different targets. So it's very, very practical. So I'm going to have hclock div. I'm not going to set any value there right now. I will have pclock1 div and pclock2 div. I'm going to explain exactly what these values mean in a bit. And we're going to have compatible. So compatible string is used for matching the right device driver with the device tree node. So in this case, we can say that this is STM32. This is, by the way, the NVIM awesomeness that shows me all of the different things here that I could autocomplete with. So let's call this STM32. This would be F4XX. We can use F4XX and we can put all the code there for all of the F4 chips. So this board is using F413, and I discovered that there are a few differences that need to be taken care of when using the F413. One of the things is that F413 is only able to run at maximum 100 megahertz. It cannot run at 168 megahertz or 180 megahertz like some other F4 chips. So using the same code that I use, for example, for F429 results in very weird behavior. It's basically like you get program that just crashes in very weird ways because it cannot load the correct values from the memory because it's running too fast. It took me a while to debug that until I finally figured out that my PLL wasn't really configuring things correctly. So I decided to invest some time in properly sorting out this clock configuration code and make sure that it's completely generic, so that I can just configure everything from the device tree. Let's create a driver for this, and we're going to move this code from system into a separate file, which will be responsible for configuring the clocks. In the device tree, things are initialized in order. So I put this section at the top, and this means that this section will be initialized first, and then the probe device drivers code will just initialize every single driver as it goes, and then it will do it recursively as well. One thing that is very simple with the device tree is configuring the GPIO pins. For example, for the serial line, I can easily reconfigure this to some other, like I can remap this UART1 to any other position where it's possible to remap this UART just by changing the device tree. I don't need to change any code, and I can have different device trees for different boards while keeping exactly the same code in the source code repository. Let me check the comments. Let's see what you guys are writing. I found my problem in my, let's see, I cannot enter in programming mode. Okay. I don't want to use Atolic IDE, I use Vim because Vim is awesome. I've used many different IDEs, and I use Visual Studio, which I hate. I used Eclipse, which I stopped using 2 days after using it. I absolutely hate it. But the only IDE, or like, I wouldn't call Vim an IDE. I would much rather say that Linux is like an IDE because it has all the tools necessary to edit code. But what I can say about Vim is that it's the only editor that doesn't get in the way. It's the only editor that I don't have to, I don't feel that I actually have an editor. I completely don't even think about the editor being there. And that I think is very important for an editor. It shouldn't get in the way at all. It should make it easy to edit code. And Vim is the only editor that fits that criteria for me. Like for somebody else, it could be something different. But for me, Vim is the only editor that I don't have to think about. So you cannot enter the programming mode. Why? What error are you getting? Are you getting this are you getting something along the lines of invalid chip ID 0 or something like that? Hello, Leonardo. All right, so I'm going to start coding this, and I'm going to create STM32 CPUC, and we're going to be placing this in F4XX folder, so we can call it just CPU. And let's see. So we just need to initialize the device driver. I'm gonna just copy the code because I can't be bothered to remember everything, all the details of the macros, and yeah. So let's see. We'll have STM32 CPU. I'm actually gonna call it CPU. So this will be called the same thing for all of the chips. Just will have different implementation depending on the chip. I think I could probably actually have the same implementation for all of the STM32s, possibly, but I'll keep them different for now because there can be some differences that need to be taken care of. Right, so we're gonna just write two static functions, and this would be STM32 CPU. Let's do probe first, void FDT. So FDT is going to be the device tree, and the FDT node is going to be the ID of the node that the probe device drivers is going to be probing when calling this function. So the way the code operates here is that it creates a linked list of all of the device drivers that are compiled into the firmware. I have been refactoring a lot of the build process that is responsible for compiling in the device drivers, because I wanted to make it more. I wanted to make sure that stuff that is not used doesn't get included. It gets a little bit tricky there though, because when you have things that automatically initialize like this, you get the problem of including too much code. Like you could, if you just compile in all of the drivers, you end up with drivers that you're not actually using, so the firmware size can increase. And I didn't want that, but I still wanted to have this automatic functionality to be able to just write a C file and not change anything anywhere else. So as long as this C file gets compiled into the firmware, it's going to actually run, and it's going to be probed on any device tree node where this code is relevant. Like any device tree node that has the compatible string equal, in this case, to STM32 CPU. So FDT node, and we want to, let's see, so we're going to return 0 here as a success, and STM32 CPU remove. I'm actually not using the remove, but it could be useful when compiling for a target like Linux, where you want to completely deinitialize all of the code when the application exits, because that allows much better code analysis using, for example, like valgrind and checking for any memory leaks. But the problem is that if you don't deinitialize your code before the executable exits, you actually end up with a lot of false positives. So it's good to deinitialize all of the code. It's not really necessary on the STM32 because it never actually exits. It just starts up and then it's running until it gets reset. And upon the reset, you just lose everything, and it's not really a problem. But I still have this it's kind of like a placeholder in most of the drivers for now, and it just does nothing. So let's see. We need to add this to. So I'm going to add this to the F4 sources. So we're going to compile that one, and then we can, let's see. So h clock div will be the h clock div. The default value, I think, I'm going to check that. H clock div. So this gets the values from the FDT section for the different clocks. And we have p clock 1 div and p clock 2 div. P clock 1 div and p clock 2 div. And what else did I have there? So, and the HEC value is currently defined on the command line, which is the standard way of doing it, and I really don't like that. I don't want to have any target-specific command line options at all, unless I really have to, which I never really have to. It's just a retarded way of doing it. I don't want to do that. So I'm going to put this here. This would be HEC value. And we're going to have to change a lot of the code that relies on the preprocessor definition of HEC value. So HEC value is the value of the crystal, basically. It's the external oscillator. So in this case, I usually use an 8 MHz crystal. It's fairly standard, and when I had the code that uses the define, I can't be bothered to change the define for different targets. Yeah. But this will make things easier. Let's see. So I will go to the system and I will copy some of the code from here. So we have the system init, which is here. And this sets up some default values for the RCC. The first thing it does, this gets called from the assembler code that is part of the loader, like the startup code, and this gets called precisely before main. So let's see here. We have the startup code in let's see, no, target's there. And we have the startup code here. So this is a startup code that I'll compile in for the STM32 F413. This basically gets placed in the beginning of the flash area. And the processor automatically then loads the stack pointer and the address of the first function it needs to call, which is the reset handler. And then the code goes to the reset handler. Does a lot of this. This is like just copied from the STM32 libraries. It initializes the data, copies things from flash into RAM for the initialized variables, and fills the BSS with 0, which is the uninitialized data, which is always good to do, because if you have any pointers that you haven't initialized, which by the way my build process will warn me about, but if there are any variables that are not initialized, then this makes sure that you don't get garbage in those values. And then it calls system init, and after that it goes directly to main, and then it just never exits the main. So currently the code that initializes the clocks is called by system init. So let's see here. So we go to system, and we have system init here. This initializes this. I think this code actually enables the FPU. I could be wrong about that. It sets the 2 bits CP. Oh, actually, CP10 and CP11. Those are the co-processors that implement the FPU, and they need to be enabled in the ARM core. to be able to use anything that uses the FPU. Like if you don't do this, I think you get a hard fault, or you get some coprocessor related fault the moment that your code starts like does some instruction that that uses the FPU. And by the way, the printf code seems to execute some of that instruction. So if you don't do this, like if you don't properly initialize the FPU, you get a very weird fault when you call printf, and it's kind of it's counterintuitive to figure out exactly what's going on, because you may not be even using any floating point in your code, but the moment you call printf, it actually just fails. And having this line is important. So the default RCC configuration uses the internal RC oscillator, which runs at 16 megahertz. And then this initializes the external memory, which is also some code that I don't want to have here. I don't want to have any code here that initializes any peripheral. But I'm going to start with clock and see where I move from there. And also the NVIC priority group config. This configures the priority of the interrupts. And I set it to 4 because the FreeRTOS code relies on the priority being set to 4. It will not work correctly if the, let's see, so it will not work correctly if the FreeRTOS interrupts are lower priority than any other interrupt handler that you have in your system. So it's I haven't actually tested running it with any other priority group, but this is kind of the way I've always been doing it. I haven't really tested what would happen if I would use some different priority group and then reconfigure, because I would have to change values in FreeRTOS as well, because it relies on using this priority group. Right, so this code just initializes the NVIC. So when we now modify the clocks, if I move this code now to a device driver, then FreeRTOS will initialize using the 16 megahertz RC oscillator. So it could actually be that we get the LED blinking much slower because, let's see, bare or FreeRTOS. Well, this is bare executable, but it uses FreeRTOS for threading, for the scheduler, basically. So when FreeRTOS starts running from the internal oscillator, it could actually misconfigure the system core clock or the SysTick, the system tick clock, which is used to schedule tasks. So things like thread sleep may not work correctly, and that's something I would have to check after I make those changes to just make sure that everything continues to run properly after the clocks are configured and the chip switches to the full speed PLL clock, which would, in this case, it should be able to run at 100 megahertz. But I've not been able to make it run on 100 megahertz. At least I don't think that I was able to do that, because when I set the clock higher than 50 megahertz, I get problems with like I get very weird faults. And I checked the flash wait states from the datasheet. As far as I know, that's configured correctly. So it must be something else, or maybe I think that I'm configuring it for a certain frequency, but the actual frequency ended up being some different frequency. So hopefully I can debug some of that as well while I move this code to the device driver. Right, so we're going to remove this. We're going to remove system core clock update. So we're going to be just running from the internal oscillator. And the functions here. So there is a global variable in the STM32 code called system core clock, and this variable gets updated after the PLL is configured. And this variable, the idea is that this variable is supposed to contain like the main the frequency of the main clock, but it's kind of deprecated because there is also code in the STM32 RCC implementation, which does exactly the same thing. It gets you the core clock, but it also gives you all of the other clocks that are used in the system. which is called the RCC get clock state, or like get clocks or something, which is the function that I would prefer my code to use instead. And I want to completely remove this code, so I'm just going to comment it out for now. So just to make sure that it's not used anywhere, and I'm going to do the same thing with system core clock variable. I don't want this variable. So now anywhere where this variable is used, I'm going to get like an error when I compile, and then I can figure out a way to remove it from all the places. So in system init, let's see, in the setSys clock, so this will go into the driver. Okay. So let's go over this code line by line, like just line by line, and just copy it and make sure that we understand exactly what it is doing. So in the probe method, we can start initializing the RCC. So first, it tries to start the external oscillator. So it sets the HEC on bit, and then it waits for the HEC to start running. So it can take a while for the external oscillator to stabilize, and this is what this code is doing. Let's see, would this be the best way to implement this wait loop? Because right, so it has like a timeout there. So now, the nice thing about being able to run this from the init process is that I can now actually use real timeouts, which in the beginning here will be based on the internal oscillator, so they will work correctly. So what we can do is let's do something similar that they are doing here. Let's see. If we'll run this while not ready, and timeout. Shall we run this for 100 loops of 10 milliseconds? Yeah. And if we have HEC, then we switch to HEC, and if we don't have HEC, then we still switch to PLL, but we use the internal oscillator instead. So if ready, actually I'm not going to use 100, that's too many. I will use 50 milliseconds. So I don't want the system to just be like paused for 1 second if for any reason it doesn't start the HEC. So if we have HEC, then we can enable the so it enables the power regulator. I wonder if it does this on both. So why does it need to enable the regulator for HEC but not power CR VOS? What is that? Let's see. I suppose that would be the RCC registers. EPB1 and R. So power enable, power interface clock enable, and then I'm pretty sure VOS is like the voltage of the internal regulator. So I think the chip can run on lower voltage internally, but you cannot run it at full speed if you decrease the voltage. And I think that when you set VOS to just this value, so when you have let's see, let's just copy this code, and then this, and the VOS value is actually both bits set. Yeah. So this sets both bits in the control register, which means it's going to be running at 3.3 volts. But let's see what this says here. This is really slow. Okay, my board have GPIO 15 low, GPIO 0 low, and it don't start in programming mode. Changing flash ESP, nothing helps. So you're using the ESP chip, right? You're not using any STM32 chips. Is it the ESP chip that is not entering into programming mode? Have you checked all of the voltages on the supply rails? Have you checked like if you have any analog voltages that the chip requires, like external VDD-A or something? So for example, STM32 will not enter into programming mode if VDD-A is not supplied. And the reset, the boot modes, also important to check. You could have some resistor which is not supposed to be there, so you end up with some undefined value on the reset pin, or an undefined value on the boot selection pins. Okay, this just crashed, so this is not getting anywhere. Come on. Firefox is struggling with a PDF file. It's 1300 pages. Okay. Can I get this loss thing? Maybe I should search for something else. maybe I should search for RCC first and then click on like the topic that's or actually power. Yeah, this is power. Oh, now I found it finally. So to correctly read data from flash memory, the number of wait states must be correctly programmed in flash access control register. So this is something I'm doing as well. When I adjust the clocks, I have to change the number of wait states, and the number of wait states depends on the frequency of the H clock, the AHB clock, and that in turn depends on the multipliers that I use for the PLL. So we are setting VOS to 1.1, which means that the maximum frequency is 100 megahertz, at least according to the datasheet. And I hope that the chip actually does support 100 megahertz and that I just misconfigured something causing me to not run at 100 megahertz. Okay, I'm gonna go back to the file and I'm gonna configure the let's have a look here. So this is actually the raw values. So this will need to be shifted if I'm gonna specify just integer values in the device tree. Eight, 9. So I'm going to check the datasheet just to get sort of a better picture of what is going on there. So H per scalar. H per scalar is right. So can we figure out some logic here? If you set it to 8, so we can basically like subtract 8 from it, and then we get values 1, 2, 3, 4, 5, 6, 7. And that translates into the different division values. Let's see. So if I just shift this, if I shift a bit to the, let's see. Right, so I can basically just shift by the number, let's see. So if I specify 4 in the device tree, then I need to find, I need to basically find just the first set bit in this value and reset all of the other bits. And there is a function for this. This is available. I've done this before somewhere. There is actually like an instruction for this, so you don't have to loop through it to find the bit. Let's see. Right, I've been using it in the GPI driver. There is a function called FFS. And FFS gives us the index of the first set bit inside an integer. In an integer value. Yeah. So we can do like this. We can go to the CPU driver, and we can use, let's see. So this will be our hpred div value, and we want to get the values that that we see here in this. Let's see. This is actually the wrong file. So there are multiple versions of this file, and I need to make sure that I have the correct one for F4 chips. So let's open up the F4 and check the hpred. So this looks a bit different from the previous file, which was actually for the F1 chips. And this makes things a lot easier, because we can just do like this. We can just specify this value exactly the way we would do it in code, but instead, let's see. Actually, that doesn't even make any sense. That would just be very confusing. I think it's better to specify actual division factor in the device tree instead of specifying some bit values. So we should just go with this. So I'll do the same implementation that I originally envisioned for this. So we have FFS of the hclock div, which will find the first bit that's set, and then we need to rotate this, or let's see, and then we need to do like 8 plus I wonder which direction FFS counts from. Is it front or back of the integer? Let's see here. Right, list significant bit. So this should return like if we specify value of 2, we should actually get 1 as a return value. And if we specify 4, we should get 3. Four, 5, 6, 7, 8, 9. And 0 is a special case. So if it is 0, then it's just 0 value there as well. Let's do like this. So 0, 80 plus this shifted by 8 bits, and -1. Am I correct here? I think it's -1 then. This should give us the value of the register that we are supposed to write. Okay, I'm just going to move on to the next one. Once I start testing this, I'll see if this is correct or not. Have you checked that that you have connection to the debug pins, like to the JTAG pins? Maybe there is, if you soldered the chip manually, maybe there is no connection between some JTAG pin and the connector where you connect your programmer. So pclock div. What do we use for the pclock? Ppre1, yes, of course. Very similar concept here, but instead we have to add like 400 and then shift this a little bit farther to the left. So pclock div will be 0x400 plus 16 FFS let's just reuse the same variables. 16 positions and -1. No, damn. This is wrong. This needs to be -1, and then it needs to be shifted. So like this. -1, and then shift this. pclock2 div. That would be ppre. This one is shifted even farther. So it would be 2000 plus 16 probably don't need to cast it in this case. So this needs to equal to 2000, and then div 4 is 2800. Wait, damn, I'm like, yeah, I'm using the wrong values for the shifts here. This is 4, and this is 8, and this is this would be would that be 11? So if we shift 1 to 8 positions, 9, 10, 11, 12. So provided this is going to end up with correct values, we could check that. We should be now able to just write this to the RCC, CGR, just OR the bits, hclock div pclock1 div and pclock2 div, and then we wait for then we configure the PLL. And this will also be supplied in the device tree. PLL-M is, let's see, is it PLL-M or PLL-N that is the multiplier? So one of them is the multiplier for the input clock, and the other one is the divisor for the input clock. So first you divide the input clock from the external oscillator, usually first you divide the clock to bring it down to between 1 and 2 megahertz, and then you multiply that clock using the VCO to get 100 megahertz. Or I think actually you get 200 megahertz, and then you divide that again to get the system clock. So it's quite an involved process, although still relatively simple compared to some other chips which have even more complex clock configurations. Let's see, so this would be PLL-M. We should be able to just supply the values for this. PLP. And this will always run on the HEC because we already checked that HEC is up and running. And PLLQ is for the USB clock. So that needs to end up being 48 megahertz. So depending on the frequency of the main clock, we need to come up with a suitable value for PLLQ to get it to 48 megahertz. And once I get this simple version running, I can actually optimize it to make sure that I don't need to specify all the parameters manually. PLM and PLM and PLQ, and this would be PLN, and I'm not specifying any default values yet, so I'm going to specify default values here. For now I just have placeholders because I haven't checked what the default values will be. Have you checked with the scope that you're actually getting the signals through? That you're getting something to the pins of the controller, and that you have the right baud rate, because that could be some issue unless it's automatically detecting the baud rate, which it probably does, but just one of the things to check. primarily to check whether you're actually getting any signals to the pins from the programmer. I see, so in NVim I cannot actually run commands properly. I cannot run any interactive stuff in NVim like this, which is not good. Anyway, let's just check this code here. Oh, damn it. Okay. Let me just switch this. I'm gonna switch from Xterm to the console terminal. So now I should be able to copy paste this. Let's say we do like that, and we can output hex. So, looking at the data sheet, yeah, so this would be equal to 90, which you would get when you supply the value of 4. And the other one here, clock 2, like this, 2000, rotate this 11, 2800 is what we're supposed to get for bpre 2. And I'm gonna just double check this against the values that are in the data sheet, in the code for this. Let's see. So that would be, yeah, that would be 2800. So this seems to be correct. This should enable the PLL, and then we wait for the PLL to start. which should actually always succeed. I don't know if there is any corner case where this can fail. And then if we are not using the HSE, then we instead use the internal oscillator. Let's see. Oh, and of course I need to set the flash wait states as well. And the flash wait states were specified in that section where you had to look like for the voltage level and correlate that with the frequency that we're running on. So I will keep this at three wait states for now, and I can experiment with that a bit later. So this goes. This is the source of the main clock, which we now set to originate from the PLL. And oh, this was really just totally useless code from the library, where they had a semicolon after the while loop, and then they had the section below it, which would never run, or actually which would always run if there was any code in there. And then this waits until the PLL is actually selected for the main clock. And for the internal oscillator, they use hard-coded values, which we don't need to actually, it could be good to be able to set the actual frequency of the chip, but the proper way to do it would actually be to specify the target frequency in the device tree, and then to calculate the necessary division values that most closely match that desired frequency. But that would be the next step. I think I'll leave this like this for now, because I'm not going to be using the internal oscillator. First of all, I'm going to be configuring the PLL from the variables that I specify in the device tree. Let's see. So the default value for PLL-M is 8, which will divide the external clock by 8 to get 1 megahertz. Default value for N is the multiplication of that 1 megahertz, which we now multiply 200 times to get 200 megahertz, which is then divided by 2 to get the frequency of the main clock, which will end up being 100 megahertz. PLLQ, let's see, we forgot actually PLLP. And Q is going to be 4. And Q is the division factor for the USB clock and a few other clocks, which has to be 48 megahertz. Which in this case it wouldn't be 48 megahertz, but we'll have to set the main clock to something like 196 or something like that. But I'll just copy the values that are specified here for now, and just until I get the driver actually running on this chip and not crashing it, and then I can go over all the values here and make sure that everything's correct. PLP, is that, I used that somewhere. Yeah, PLP. So this translates the PLP value to the bits that need to be written to the register. Okay. So we should be able to run this now. I'll just add this, I'll include this device driver into my firmware, which I can do here. Let's see. I've done some refactoring to how I'm actually including things into the main firmware, which is probably not perfect, but it's a bit better than what I had before. So let's add actually no, this will go into the default. Yeah. Let's see. Would it be? Actually, yeah, it's going to be like this. STM32 4XX, STM32 4XX, RC. Much better. And the default values for this, of course. So H clock needs to be set to, let's see, system. This is a header file. Let's go to system H. And let's set this to 2. 2 for number 1 and 1 for number 2. And this would be 8. So right now it should compile fine, hopefully in just a little bit. Include thread. Ah, I see. Yeah, let's make this unit 32s actually. Actually, all of them. They're never negative, so it makes sense to make them unsigned integers. each clock div is conversion to int from uint32. Yep. And the HSE value is unused. Let's comment it out for now. We have a syntax error in the device tree. Which is not surprising. So we'll set hclock divisor to 2, and this would be 2, and this would be 1. Oh, of course. Right, undefined reference to system core clock, and that's referenced from setup timer interrupt. And this is actually something that will need to be reconfigured after we switch to PLL. So this will need to be called from the driver to reconfigure the clocks. But the config, this is defined to be system core clock, which should actually not be a variable. It should be so it gets a little bit tricky with the dependencies here. We have FreeRTOS depends on no, actually FreeRTOS shouldn't depend on anything, but then it gets the core clock from outside as a global variable. So it's kind of weird direction of dependencies. But the simplest way to, without making too many changes to this, is to just define the system core clock and set it somewhere. Let's see. Was that the only way? Was that the only place where the system core clock was used? I think so. So. I will define the system core clock, even though I don't like global variables. I think global variables should never be used. But in this case, it's just this will need to be removed. Yeah. No, actually, I'm going to set this to 16 by default. And this doesn't really need to have any initialization value because it should be set here. It should be set like this: rcc get clocks freak clocks. And this would be rcc clocks def system for clock equals clocks sys clock frequency. Some kind of crap like this. And then this will need to be used from the FreeRTOS. Int32. Let's see. So it's running. It's actually running. Question is if it's actually running the new code, or if for some reason, for whatever reason at all, I flashed some older code to it. So I'm going to check this. I'll just show that it's running. It's blinking a LED, so it's running the blinker task. So it means that the system is alive. But we'll check to make sure that this actually runs the correct code. Let's see. We can do right. It's running the new code, so it seems to be working. But I'll check what values I get for the clocks. But I need to update my GDB file, the script that I'm using. So I'm using a small script that just runs. Let's see. I set the breakpoint on RCC get clock freaks, and then I continue and I finish that function so that I get out of that function. Which means that I should be ending up at a place right after the call to get clocks. Let's run this again. And now we should be able to print clocks. Right. So we're running at H clock frequency 25 megahertz, P clock 25, everything else 25. Let's see. And sys clock is set to 100. So why are we getting 25? I think we're writing the wrong values to the registers. Okay, so you're getting default baud rate 74,800. Interesting. Interesting default. Maybe it's your fault, maybe not. Okay, so I need to go back to the, let's see, maybe I can actually step this. So I'm just, let's see. So I'm just after, I'm just at the end of this function now. Anything that I could check here? I could probably check the RCC. Let's see, what symbols do we have? What can I check in the current state of execution? RCC, I should be able to check the registers. Let's see. Oh, I should be running without any optimization when I fire up GDB, because all of the values are going to be optimized out. So without recompiling this, without doing anything else, can we figure out what's wrong with this? So this is going to is there anything that's missing? So I should be getting the default on these variables anyway, so this shouldn't be an issue. PLLN is 200. PLLP is 2. PLLQ is 4. So we're getting, we get basically HEC value, so system clock equals HEC value divided by PLLM times PLLN, and then the H clock becomes sys clock divided by H clock div. Yeah, I think that should be how it actually works. But there's still something wrong with the values. Let's just rerun this. Yeah. I should just run it to a line, but just can't be bothered. I'm almost there. So So hclock div is 90 and the pclock1 div is 500, which doesn't seem right. And that's 200. Let's check with the datasheet. Okay, it's actually easier to just check from the definitions that are used for this. I get the definition of this H. So we have that at 90, so that means it's actually divided by 4. So that's not correct. Wait, maybe I was wrong about the return value of FFS. Just position of the first bit set in the word. The listener bit is position 1. Okay, and the most significant position is, for example, 32 or 64. And return value 0 if no bits are set. So I was wrong about the return value of that. So I made a wrong assumption here. I should have just done like this. Shit happens. Oh, I have the STUtil running, so I cannot flash. Okay. Let's quit this and restart STUtil and then rerun the script. So now we're at like 12.5 instead. Oh. Did I just do the wrong change here? I think I should have been doing like this. Right, so if we have a value specified as 2, then we get 2 from the FFS function. But we need to just set so yeah. We need to also handle the we need to handle the 0 as well. So if we have 2, then we get the 80 as value. And if we set the if we do if we specify 4, then we have the third bit set. So we end up with setting 1 bit, so we get 90. Yes, this should be the correct way of doing this. But if it is 1, then we set this to 0. So this is now running on the correct frequencies, which I've been running on before making this change of moving the clock initialization into a driver. But for some reason I cannot make it run on H clock of 100 megahertz. This is actually, I should be getting some, I should be getting H clock. Did I specify H clock as divisor 2? Right. So that's why I'm having 50 there. So if I specify H clock to run at 100 megahertz, and I specify the P clock 1 to run, is it actually P clock 1 or P clock 2 that supports only 50? Right, so P clock 1 cannot exceed 50 megahertz. So we need to make sure that P clock 1 is at most 50 megahertz. So now we'll have H clock. So I wonder if the value is correct for P clock 1, because when I was dividing the H clock to bring down to 50, then this value should also be derived probably from the system clock and not H clock, which means that we can keep that at 2, so that we get we still should get 50 megahertz there. And P clock 2 this doesn't make sense. So P clock 2 was actually 50 megahertz, so that must imply that it's either wrong in the initialization or it's derived from H clock. I think P clock 1 code is actually wrong. I'm gonna check. So CPU. Let's build this and see what we end up with. It's not running. Which makes sense because the frequencies are now incorrect here. So peak clock 1 is definitely not being set correctly. Peak clock 1 needs to be 400 and then specify 2 there, so we should get value of 2 minus 2 becomes 0, and then we just right. So what is the value that needs to be set here? I see. That explains why I'm getting wrong values here. So it's not actually 8. These are reserved. So it's supposed to be this one will be 10 and this one will be 13. Yeah. Maybe now I'm going to be writing the correct values to the registers. And I forget always to stop that. Let's see. Most likely it won't run because it never runs at any values that are beyond 50 megahertz. So it doesn't run. But we can still run this. Yeah, GDB always does that. No idea why. So I always have to restart it. P clocks. Still wrong values. Right. Of course. So let's see. So we have that, and then we have should actually be using value of 1, 0 there. It doesn't matter really. Anyway, so 1, 0. And this one is then actually 8 instead. Like this. This looks correct. So now it's supposed to be running at it's supposed to try to run at 100 megahertz of H clock frequency, and P clock 1 is correctly set to lower frequency of 50 megahertz, and P clock 2 is at 100 megahertz. But it doesn't run. It doesn't run on these frequencies, and I haven't figured out why it doesn't run. It just works on frequencies that are lower than that. So let's see. So H clock needs to be divided by 2. And then we can keep that at 1. Maybe I'm configuring this wrong, actually. Let's just make sure that this runs correctly. If this runs correctly, then I'll attempt changing the prescaler values so that I don't multiply by 200. Yeah, this one runs, but it runs very quickly. So it's clear that FreeRTOS is not updating the system tick timer periods. So let's make sure that it does. Let's make sure that we have some code here that can call that. I think it was the private function that So vport setup timer interrupt. Can we call this from? Let's see. Just to make sure that we have an interface that doesn't depend on FreeRTOS headers. And then let's see. And after we've done this, we can call thread update clocks. Why am I not? Why is the code not seeing this? Ah, of course, because this code is part of libfirmware, so it should be actually using the default header locations and not the installed header locations. Other parts of the code, other libraries, other drivers, they should use the installed locations, while any code that's part of libfirmware should be using the internal locations. Port setup timer interrupt. So let's see if this function is defined somewhere. Yeah, let's just define this function here. It's only used in this file, so we just need to make sure that we can find it. Yeah. Now it's running, but it's running actually slower. It's not, let's see. It's blinking, but it's not running at the required speed. So before it was running too fast, and now it's running too slow. So for some reason, this doesn't quite update everything that needs to be updated after changing clock speed at real time. Which is something I do need to figure out, because if I want to change the clock speed while the processor is running, for example, to save energy, then I need to have a working solution for the scheduler, so that it doesn't suddenly start running slower or faster. Oh damn. Did my live stream just die? It's still streaming. What is going on? Okay, it must have been just YouTube. Okay, the live stream seems to be fine. So, sys clock frequency, and then maybe it's not. Maybe something goes wrong when I try to update this while the SysTick is running. Because this is where it enables the SysTick for the first time. It does sound reasonable that I maybe need to disable the SysTick before actually changing the settings. So let's reset all these bits here. Nope. So reset the bits, then update the reload register, and this will be so I'm thinking this may actually be 100 megahertz, while the system is actually running at 50 megahertz. Could that be the problem? I'm going to check this clock diagram that they have in the beginning here. This is the clock diagram of the STM32 F413 chips. And so we get our HEC frequency of 8 megahertz. It goes to the clock source control, or actually it gets selected here. So we select the HEC value as HEC clock as being the source for all the other clocks. And then we get system clock, which goes to the AHP. So this is the H prescaler, HPresc. And SysTick clock is for some reason divided by 8. But this, so SysTick comes actually after the AHB prescaler, which means that should it possibly be using a different value for the clock. So maybe I should be setting this to not sys clock frequency, but instead I probably should be setting this to H clock frequency. Because sys clock is the input to AHB prescaler, and the SysTick clock is originating from that prescaler. So it makes no sense to use sys clock frequency for that. I think it definitely should be H clock, if that's even correct, because it's also supposedly divided by 8. I'll get this straightened out with the global variable. I really don't like having that global sys clock variable. Right, so this actually worked much better. So now it seems to be blinking at the correct rate. So that's fixed, but we still have this really ugly global variable that shouldn't be there. Probably the cleanest way to get this out. I'm not going to modify these files now, so I delete my changes. I want to keep them as clean as possible without any modifications, just straight from the FreeRTOS source code. But what I do want to do is maybe I should have the whole clocks variable. It's not really the best solution either. I mean, it's just swapping out one bullshit for another. I don't want to have any global variables, but in this case, it's kind of the way they designed the FreeRTOS. Or maybe, actually, maybe, just maybe, the correct way to do this is to actually redefine this function. Because it's defined as weak, so that means that we can redefine this function. And we can actually put this function here. We could actually have use the correct value here. But then this would need to depend on FreeRTOS. So this is not really what I want. Nope. And I don't want FreeRTOS to depend on any chip-specific code. So it has to be, if it's going to be anywhere, this function, then it has to be here. So if I can live without tickless idle, I could actually delete this part. Or I could actually make this dependent on FreeRTOS. Yeah, that's probably better. So include this is going to be very messy. Because this also needs to include the config. And the config depends kind of on the target. Yeah, this may not even compile, but let me check. So if I just compile this, do I get, yeah, that's undefined, so we do need the port. Let's see here, we have kernel include portable, yeah, so portable, maybe if I include portable I can use these variables. Let's see. Nope. There isn't really any way around this besides just including that port, which in this case it's really ugly solution, but it's never going to be the case that this will depend on any other port, because this is STM32F4. So we should be able to just include the port, and that would be in, or maybe can I include directly just the, if I have the include path specified on my compile command line, then I should be able to include FreeRTOS config. And this then includes the system STM32F4. Yeah, it's totally, it's a complete mess when dependencies have to be done in this way. Right, so port macro, is that the, yeah, this should contain all of the different, this one is, right, so I should be able to include just FreeRTOS config and port macro. So where the hell is it defined? It's defined here. I see. Okay, yeah. This should really just be using the RCC references, the global references for RCC registers, and not go through any of that crap that's only defined in port C. But the question is then what this would be called in the RCC definition. So let's go to include here and to RCC. What is the load register? Is that? Can I find the reference for SysTick here? Okay, so it can either work with a clock that's divided by 8, or it can work with a Cortex clock, H clock, which is probably what we want. But where is the load register? I think that all of this RCC stuff is actually specified in the ARM manual. It's not going to be in this reference manual. Instead, I have to look at the reference manual for the Cortex M4 core, which I'll have to find as well. And it's probably easier to just try to figure out what the hell this register is called in the Cortex M4 code. So SysTick load, where can that be? So This is probably defined in CM4. Okay, I can be bothered to try to translate this to the CMSys variables. I'll just copy this and use it as it is. And this will just go to this file. Right, so system core clock is no longer there, which means that we need to do like this. So now we can actually combine this with the STM32 code and get the correct value to set here. So config clock hertz, SysTick clock hertz would be clocks H clock. This function is no longer needed. Instead, I'll just call this function directly then. Yep, and this is working. So, great. This simplifies a lot of things when it comes to porting this application to different, or this system as a whole, to different boards. And now I can actually also change this. So, I prefer to stop the interrupts before I make any changes to the registers. So I'll do it like this. And that's it. That's it for this video. I hope you learned something. So, your logic analyzer has been destroyed. Do you have any idea why? Maybe you have some short somewhere that feeds some higher voltage to the debugger pins or something. Actually, I'm curious about this. I'm gonna check ESP8266. I've heard all the hype about them, but I never actually got on one or experimented with one. I have precisely that module in a drawer. Node MCU. So how do you actually flash it? Do you flash it over UART? or do you have a JTAG interface connected? It seems simple enough, but I suppose that you probably need to boot it into ROM to be able to flash it. I can't imagine that it will automatically just boot into the bootloader, or maybe it does. Maybe it boots into the bootloader and then waits a little bit there, and then continues. But it won't surprise me if it actually needs to be somehow put into boot mode before you can flash the firmware. So are you setting GPIO 0 to 0 and GPIO 2 to 1? Alright, have to go now.